so it's let me see how I share the share screen, and let's go for the log normal. From now on, I will spend probably this lecture and a little bit of the next lectures in describing what is the kind of process which leads to the various distributions which we encountered. Can you see this new presentation which I loaded now?
Yes.
Okay, good. So so now I'm normally I should have started with the process, with the dynamics which illustrate how the normal distribution appears. But first of all, more or less we have seen it in previous lectures. And secondly, I wanted to a little bit perversely to rub it in that that the inequality in wealth it's actually a relatively normal thing, and it shouldn't be a big surprise for anybody. So I'm discussing the following process. And for simplicity, of course, I take very few people, let's say 64 people. And you will see why I take 64, because it divides many times by 2. And then the rule of the game is following, that at each reiteration of the timing, let's say every year or every second, there is a probability that for each of the participants that he or she will double its wealth with probability half, but it might actually lose half of its wealth with probability half. Now, this is, of course, if you think in terms of playing the stock market, that is basically what the stock market is. Unless you are an inside trader and you know something which nobody else knows, then it's like this. You can lose with some probability, some factor of what you have invested or gain. But the way I think about it, it's true probably also when in life, even for people before history. Let's say if you could think of trying to attack a rabbit and eat it, and that would be a relatively you cannot really get hurt very much by a rabbit. Of course, you can get hurt if you run after it and after the rabbit and you fall. But if you put in your mind to chase a mammoth or a big lions of the prehistory, then this might cost you your life. On the other hand, if you bring a mammoth to the rest of the tribe, everybody will respect you. Maybe they will elect you the president of the tribe or something. So this mechanism by which you can gain or lose proportional to what you have already have, it's quite general. If I need to defend more the realism of this kind of thinking, please let me know, and I will try to argue. Now, if nobody asks me, then I will go ahead with describing to you what happens if such a process takes place. Now we start with everybody equal. We, as I told you, in addition to arithmetical thing. I'm trying to make a point about the emergence of inequality in wealth. So even if we start with everybody equal, and even if everybody has at each particular moment an equal probability to gain or to lose, so we are excluding from this game any, people doing unfair things, then you will see that still we will end up with quite an unequal spread of the wealth. So after the first moment, the first round, so to speak, as I said, half will have double 64, which is 128, and half will have half 64, which is $32. Until now, it is clear, Raham?
Yes, let me just repeat after you. Like people have the same probability to earn money and lose money, right? That's what you mean. Okay. Yes. Cool.
Okay, so this is after one iteration of the game. Now, the next iteration of the game is that each of the 32, let's say the 32 which have $32, half of them will have $16, and half of them will gain, will double their wealth and will have $64. While the guys which have 128, again, some of them half will double, which is 256, and half of them will lose, and they will get 64. And this way, 64 will get half from the 32 and half from the 128. And so in total, there will be half 32 plus half 32. There will be 32 people having $64. And there will be this one which lost twice. First, they lost from 64 to 32, and then from 32 to 16. And there are 16 of them. And there are 16 people which gained twice and got 256. And after another iteration, what will happen is that let's say these guys which lost twice, some of them will lose again and will get from 16 to $8, and some will gain this time, which means they will go to. There is something here with the computer, but doesn't matter. So some of this 16 which lost twice, this time they might gain, and they will get to 32. So out of the 16, 8 will go to $8, and 8 will go to $32. But these guys which at $32, they will also get a contribution from the guys which lost once and gained once and have now $64. And there are 32 of them, half of them, 16, will go to 32. So this means that at 32, I will have 32 divided by 2 plus 16 divided by 2 will be 24. And there will be this 8 for the $8, and there will be, I didn't make the computation, but you can believe me that at 128, there will be also 24, and the guys which gained 3 times, the probability to gain once it's half, the probability to gain twice it's half times half, 1/4, and the probability to gain 3 times it's 1/8. So 64 divided by 8, it's 8. So this is what is the distribution of wealth now, which is already quite unequal, because there are people which have 300. What is this? No, 512. I cannot say, yes, 512 here. And there are some people who have only $8, and it's a big factor. between how much they have. And if we go to the next stage in the game, again, we'll have this guy from the 8, which lost 3 times. Now some of them will, half of them will lose another time, and they will be left with $4. And the guys which had 512, they half of them will be able will win again, and they will have 1,024. And the others will get again contributions from the neighboring values. And now you see why is this kind of distribution called log normal? Because on one hand it looks like a normal distribution, but it's on this kind of scale in which equal distances are representing equal factors between the various values. And we can continue this way and more steps. In principle, one can go on and get to half $1. These guys which are left with $1, if I play again, then I will be left with some of them will actually, the way I chose the numbers already, there is not only fractions of dollars, but fractions of people. So this is why, in fact, I don't continue. But you already got the principle. And of course, if I started with millions of people, and then I will be able to go on with this, and this shape will look more and more like a bell, but on a scale which is very different than a normal scale, because you see the largest value on this graph, it's people having more than $4,000, and on the other hand, there is this guy which has $1. So you see that this was a game which I deliberately took it very fair. Everybody started with the same amount, and everybody had the same chance to gain or to win. And still, we got to very different outputs between different participants. Now, my comparison at the beginning that one could go and hunt mammoths or some other animals and gain, and some will not get the mammoth, or might even get hurt. That is not a perfect comparison, because there you might say that it was related with how talented was that person at hunting mammoths. While in this particular game, we put it by hand that everybody at each stage had exactly the same chance to win or to lose. It's not related to their capabilities or something. So this already shows that one can end up with a very unequal distribution of wealth, even if the game is it's fair. Okay, so I said this. Now, this slide is another way for me to excuse myself that I'm using this scale, because it shows that if I was using the normal scale, in which the differences between different points, the distances are equal to their difference, then already the difference between 1 and $4, if I take it a reasonable distance, already 16 is getting out of my scale. So not only it was very natural to use that scale, because in any case, according to the rules, there could be no other values of the wealth except that multiples of 2. But it also shows that one can show on the same screen the various values. Now, a few comments about this game, because I don't know how convincing I was that this is a good metaphor, so to speak, about how the wealth of in real life has a dynamics. But one could ask, suppose that this was this is how things happen into a real stock market. Then you might say, well, maybe it's not such a good idea to have stock markets at all if people have equal probability to lose or to gain. But the point is that is not really true, because you see, when in terms of the society, if somebody loses half and somebody else gains twice, then the average between them it's gaining, because let's say 2 plus half, it's 2.5, and minus how they had before, 1 and 1, there is 1/2 which the society gained. So this kind of market, even though somebody gains and somebody loses, it might lead to a situation in which the society as a group it's gaining. So in fact, the inventor of economics said when he started to understand this kind of things, he said that this system of investing of capitalism is so wonderful, because even if people are egoistic and each of them are behaving for his own interest, the society is still gaining from it. Of course, there are limits to this. Now, let me now go to the next presentation. In the meantime, are there questions or disagreements or comments? If not, then I will go to actually the normal distribution. We already discussed something very similar, but maybe it's not so bad to speak again about this. Okay. Slideshow at the beginning. So this set of I'm sorry. I think that the narration was here. I put the narration because some of the students told me that they would like to have the PowerPoint presented either by email or by uploading to the course. So I prepared also sound narration in addition to me giving the lecture. Of course, in a sense, it would have been natural for me to give first this game, which leads to the Gaussian distribution, not to the normal distribution, because it's, so to speak, simpler. But I wanted to make the points which I made before. So now we have a different game. So essentially what I'm doing here now in this lecture, and maybe it will go to the next lectures too, is to present to you, so to speak, arithmetic metaphors about how one gets to the various distributions which we have discussed until now. So we have discussed the normal distribution and the log normal distribution and the power law distribution. So the power law will be a little bit more difficult. So I'm starting to get you accustomed with these processes which create the normal distribution and the log normal. And once you understand how they are obtained by this kind of dynamics, then it will be hopefully easier to understand how the power law can emerge from a very similar type of dynamics. For me, it's very pleasant that the same kind of very simple explanations which I'm giving by these PowerPoints, which are definitely, as promised, not mathematics, can be used to obtain the power laws, which for many years I was giving talks to scientists which knew a lot of mathematics about this, because it looked like you need a lot of mathematics to do that, and it turns out that you don't. And this is why I give this course to Avnei Pina. So the game which this time we are taking into account, we start again with 64 people, and again each of them have $64. Except that now, when they are gaining, they can gain $1 with probability half, and they can lose $1 with probability half. So the probability of gaining or losing is the same like before, but now the quantity is a fixed quantity. It's $1 rather than a percentage or a fraction of what they already have. So basically, the point I'm trying to make is how different these two rules are between having a fixed quantity or having a fixed factor by which you can gain or to lose. So if we start playing this game, in terms of pictures, they are very similar with the previous one. The guys which had 64, half of them will lose, and they will have 63, and half of them will gain and will have 65. Of course, much less than before. Before it was 128 and 32, but on the picture it looks very similar. And again, if I play again the game, out of the 32 which have 63, half of them will get 62 because they will lose, and half of them they will return to 64 because they gain back what they lost. So after 2 steps, we'll have 16 people which lost twice, and they have $62. There will be these people which gain once and lost once, and they are 32 because there could be the first they lost and then they gained, or there could be the first they gained and then they lost. So and then there are 16 which are the ones which gained twice. And of course this can go on, and the numbers are the same like in the case of the multiplicative what I call multiplicative random walk. But you understand what I mean. It's random walk. It's one can go to the right or to the left with the same probability. And but the difference is now that even after I get to the end of the story, because I don't want to speak about fractions of people, the difference between the wealthiest and the poorest, it's this time much smaller. Before, you remember, it was 4,000 against 1, and now it's between 70 and 58. So this kind of game in which the gains and the losses are additive, it's much more leading to a kind of egalitarian distribution of wealth. You might say yes, because there is only $1. But even if it would be much more fixed quantity, when you take the game more and more times, the richest will get richest proportional with the number of times, while and the poorer too. While in the multiplicative case, the richest doubles each time its wealth. So even if the differences will be bigger than $1 in this game, the additive game leads to much more egalitarian distribution of the wealth. And this is a normal distribution. And this is what is written here. It's what I said before. So I'm finished with this presentation too. And again, I'm asking for questions, comments. Or everybody understood? Okay, so now I'm going to the next thing, to another game, which is slowly I'm preparing the way to getting the power law, but meantime I'm showing a game which leads to something which is called an exponential distribution. Sorry. Wow. Just a second. Share screen, exponential, share. Is it showing? Yes, now it's showing. Okay, can you see the new presentation?
Yes.
Okay, good. So let me. This one is a little bit more complicated. I mean, the previous ones were maybe a little bit boring, but I made them. I still went through them because I wanted to not to throw you directly into this presentation, which is a little bit more complicated. So now I'm doing a game which is as close as possible to the previous one, but a little bit more complicated. So I start with 1,111 participants, and they have all of them $0. and each time step, each of them can earn $1 with probability 1/10. Is the rule clear, David?
Yes.
Okay, good. So I'm playing with again. It's not by chance. This is how why I played before with this blue rectangles, because I wanted to prepare this game. So I have now all the 1,111 with $0, but 1/10 of them can get $1. So the next step of the game, there will be 1/10 of 1,111, which is 111. That they are that they gained that $1. So now the distribution is like this. There are the ones which didn't earn anything, the 1,000 are left here, and then there are 111 which have $1, and I'm now saying sincerely that in principle 1/10 of 1,111, it's 111.01, but I'm neglecting parts of people. So and I promise you that this is not. How should I say? It's not leading to incorrect results. It's just that I'm trying to save you complications with parts of people. So now we can play again and say, okay, but these guys which got $1, they can also gain one more $1, and 1/10 of them, which is 11. So they will have this, and then the guys which have $2 now have a chance of 1/10 to get one more. So in the end, you see that I get a distribution, which is like this. There will be 1,000 people with $0, 100 people with $1, 10 people with $2, and one person with $3. And this is called an exponential distribution. I will use that term, even though as I told you, I think that many of the situations in which people which work in some subjects, they give names in order to give themselves more importance and to show the others that they know and that the others don't know and they know. But in this particular case, it's not so so complicated. I'm sure that some of you understand that dividing each time by 10, it's essentially 10 to the -1 and 10 to the -2 and 10 to the -3, and these are exponents. So this distribution is called exponential because when I go to from one wealth to the other, I go to another exponent of 10. So it's 1,000, and then if I go to wealth of 1, it's 10 to the -1, which is 0.1, and so I get to 10 times less than 1,000, it's 100, and then it's 10 times less than 100, it's 10, and then it's 1. So this is called an exponential distribution. Are there people which have difficulties to follow up until now? No. So So now this is a pretty simple thing, but suppose that that now I want to fight the inequality because it's not a big inequality because the richest one has $3 and it's only $3 more than the poorer people. But suppose from what we have seen until now, when we'll go to the multiplier, this is the process which we are discussing now. It's additive. Each time I was adding $1. But when we'll get to a multiplicative one, we'll have much bigger inequality. So I'm showing how to fight inequality in this simple model, and then we'll see that when we fight inequality in the multiplicative process, we'll get the power law. So now we introduce to this process social security, and we say if a participant is poorer than $2 from the richest, then he will be given such that it has just $2 less than the richest. So we introduce a rule that if somebody is so poor that that is $3 less, more than $2 less than the richest, then it will automatically be given enough to have only $2 less than the one. So what that means? It means that all the guys which have $0, they will get promoted to $1 by this rule. It's a kind of social security applied to this model, which is not yet very realistic. You'll see that slowly we'll get to more realistic models, but I want to go in small steps to be sure that I don't lose a student. As I told you, since I'm giving this course, and it's quite a number of years, I'm losing less and less students. In the first year, it started with 40, and I was left in the end with 6 or something. And my ambition is that this year I will not lose anybody. So we get by this social security rule, we get to 1,100 which have $1, because 100 already had $1, and we get the 1,000 which has $0. We gave them $1. So now we apply again so to speak, you can imagine that when I'm saying that, and now we also change the rule that instead of having a probability 1/10 to gain $1, now people will have only 1/11 because supposedly, in order to give money to the poor, one has to take from the others. So now not only we have the rule, or the social security rule, that nobody is allowed to have less than $2 than the richest, but in addition to this, we have a small change in the rule that the probability to earn $1 in place of being 1/10, which we had before, will be from now on 1/11. So with this rule, it means that the guys which have $1 will have probability 1/11 to get to $2, and 1/11 from 1,100, it's of course 100, and therefore the number of people, so 100 of the people which have $1 will have now $2. So we have together with the 10 people which had already $2 will be 110 people which have $2, and there will be left with 1,000 the people which have $1. And now the guys which have $2 will have a probability, each of them to gain $1 with a probability 1/11. So there will be 10 people like this. So and 100 will be left with $2. And now there will be 11 people with $3, 100 people with $2, and 1,000 people with $1. And now the number with the guys with $3 would have a probability to gain $1 each of them, which is just one person out of 11. So we are now, look, what nice. We are basically, after having an entire tour of applying these rules of gaining money, earning money, and also giving subsidies to the poorest, we are left with a situation which is again an exponential. Each time that I increase the wealth by $1, the number of people having that wealth decreases by a factor of 10. So it's again an exponential, like before. It only starts at $1 instead of starting at $0. So already you see that one can, of course, this is another distribution, not the power law distribution, but it becomes pretty clear that if I apply the rules of this kind of rules of the game, I can have a quite stable shape of the distribution of wealth, even though the total wealth of people increases. But the distribution of wealth, it doesn't change. That's good news, because you see, one of the problems with the Pareto law, with the power law in wealth, was that how come that he discovered it in 1896, and in the meantime there were big wars and big economic crisis, and through all this, in the end, the Pareto law was preserved until this very day that we are still speaking about it. And here you see that in spite of the fact that there is a dynamics and a change in the distribution of wealth, the shape of the distribution of wealth does not change. Of course, it's a power law, it's an exponential law rather than power, so we'll have to invent a slightly different model. But in the meantime, I wanted to get you accustomed with this. So again, it's called exponential because if I start with with 1,000 people having $1, then it's 10,000 times 10 to the minus 1, and then $2 it's 10,000 multiplied by 10 to the minus 2, which means just slicing two zeros from the 10,000, and so on. This is slicing 3 zeros, and this is slicing 4 zeros, and this is the exponent. It's called exponent. It's again name. You don't feel to feel threatened or scared by the fact that maybe some of you didn't know that, because there is not much to know. These are names. Okay. So of course, this can start again, because now we are in a situation in which we have to apply the Social Security law, because now there are people, in fact, very many of them, 1,000, which have more than $3 less than the richest. So according to our rule, we have to they have to receive $1 each of them. So in place of of having 1,000 people with $1 and 100 people with $2, we'll have 1,100 people with $2. And again, now some of them, 1/11 of them, will get $1 more, and so on. And so we'll get, after applying many times these rules, we'll still be left with this factor of 1,110 and 1, except that after each round of the entire system, everybody gets more dollars. But the distribution will stay an exponential distribution. Okay, so we are finished with that presentation too. And again, you have the opportunity to stop me and to ask me questions, because now we are supposed to get to something more important, which is describing how you get to a power law to this. So where is the power law? Okay, it's this one, I think. Yes. So sorry. Is sharing, yes?
Yes.
Okay, good. So let me slideshow. Let me switch off the sound. And now we are getting to multiplicative law, and in which we will have a similar dynamics about preventing too poor people to be too poor. Like you remember that when we described the multiplicative law, we got to a situation that the richest got to 4,000 and then the poorer was to 1. And if we had more people and more iterations of the game, we would have gotten to arbitrarily large differences between the poorest and richest. In fact, as I said, the richest would go exponentially rich, and the poorest would get exponentially poor, and that would be not a very desirable thing. So what we'll do now, we'll make again multiplicative process, but we'll have a kind of social security as we had for the additive process. So again, we start with 1,111 participants, which have $1 this time. Because if we want to have multiplicative, we cannot start with 0, because 0 times anything stays 0. So there is nothing interesting that can happen there. At each time step, each participant can multiply its wealth by 10 with probability 1/10 at the beginning. So we start with $1, 1,111 people, and there would be 1/10 of them which will gain $10. So there will be 111 people which have $10. And if we apply this rule to them, then there will be 11 people, 1/10 of them which will get to $100, will multiply their wealth by 10. And then out of the 11, there will be 1, basically. It's strictly speaking, it's 1.1 people, but since we don't want to deal with parts of people, then it could be one person which have $1,000. So already you see that with this kind of dynamics, we'll get again at each wealth which we are considering, there will be 10 times less people, except that now the wealth, in place of being 1, 2, 3, and 4, it's 1, 10, 100, and 1,000. So, so this is already a power law in the sense that if I start with 1,000, 1,000 times the power minus 1 of 10, it's essentially 1,000 divided by 10, it's 100. And then if I go to 10 times more wealth, then it's 10 times less people. So this is a power law exactly in the sense in which we described even at the beginning of this lecture. Is there anybody which does not recognize this as a power law? David? Tebsana? Okay. Gamara? Okay, I see.
Yes, yes, we understood. Thank you.
So already we have a power law, but if we keep doing like this, then this power law would become more and more, how should I say, unequal. The situation will become unequal, as we have seen in the example of the log normal distribution. So therefore, we introduced Social Security. So we are saying if somebody, it's of course there are very few people here. So in place of having Social Security like in the real world, in which even after one takes the Social Security, the poorest are much poorer than Bezos. We are taking in this model that if somebody is poorer by a factor of more than 100 from the richest, then it will be subsidized to get exactly 100 from the richest, which is actually milder. I remember that they wanted to introduce a law in Israel, especially in the banking, because the bankers were the leaders of the banks had very big salaries, so they said that it may be legal that they would have more than I think 40 times the poorest, something like that. And of course, the result was that the head of the banks resigned, and they went in the private sector, and they are still earning a lot. But if we have this law, then everybody which had $1 has less than 100 of the richest, which is $1,000. So they are given $10, so that they will have only 100 times less than the richest. So there will be in place of 100 people with $10, there will be 1,100 people with $10. And as we did before, now the probability for gaining, for earning 10 times more is reduced. In place of being 1/10, is now 1/11, because some money has to come from some place in order to subsidize. So now there are 1,100 people with $10, and out of them 11 1 over 11 will gain 10 times more, which is 100. So this means that the number of people with 100, in place of being 10, it's now 110, and there will be only 1,000 rather than 100 and 100, 1,100 with $10. And now the guys which have 100, 1 over 11 of them will get 10 times more. So that now there will be 11 people with 1,000. And out of them, one of them will get to 10,000. So you see that we are back to this situation in which the number of people having a certain wealth is inverse proportional to the wealth itself. So when the wealth is increasing by 10, the number of people is decreasing by 10, and this is how it can continue, because now we have to apply the social security to the people which have $10, because there is somebody which has $10,000, and according to the rules which we put, nobody should be allowed to have less than 1/100 of the richest. So the guys with $10 are subsidized to get $100, which is 1/100 of the richest, which has 10,000. So then we get to the fact that the number of people with 100 will be now 1,100, but some of them will get even more. And this power law will be reproduced after all these gains and social security are applied. So, so not only that we understand by this, so to speak, caricature model, how come that one can get the power law, but we also can understand how come that the power law is stable even when the society changes and the wealth of people increases. I'm not showing here about the decrease, but let me put it this way. There was a big effort to translate the kind of models which we constructed and which had some mathematics in them into this kind of very visual explanations, which hopefully gave you within actually very short time this information, which I find it very important, both in terms of what I was hopefully succeeded to show to you, that if you have a multiplicative process, then you get even for a very fair game, you get a large inequality. And when you try to fix this inequality to a certain level by having subsidies, then you are ending up with a power law.